In a universe still young and restless, a single star ignites in the farthest reaches of cosmic time. It hangs inside a primordial galaxy wrapped in clouds of hydrogen and helium, burning with a blue-white fury no human eye will ever see directly. From its surface, trillions of photons are released every second, spilling outward in all directions like a silent storm of messengers. Each particle of light carries a record of that instant. The star's temperature, its chemistry, its trembling birth inside a newborn cosmos still thick with darkness. As the eons pass, the fabric of space-time stretches. Galaxies drift apart, clusters condense, and invisible halos of dark matter grow around them like ghostly scaffolding. The star's light is caught in this evolving architecture. It is bent around massive clusters, delayed by warped space-time, split into multiple paths by gravity itself. What began as a straight journey becomes a maze. Some photons take the long road, looping around distant masses. Others slip through narrower valleys of curvature, arriving sooner. The universe, without intention, has built a hall of mirrors out of gravity alone, far in the future. In a quiet control room, on a small planet orbiting an ordinary star, astronomers stare at the echoes of that ancient light. On their screens, two tiny points appear in the same lensed field, one fierce and young, one softened and aged. The data insist they are one and the same star. Seen in two different moments of its life, a question settles over the room like a chill. How can a single star appear in two ages at once, as if it remembers its own birth and confesses it, line by line? In the spectrum that now horrifies those who know how precisely light tells the truth, it begins not with a single star, but with a map. High above the Earth, an infrared space telescope drifts in a cold halo orbit, far from the planet's heat and scattered light. Its mirrors are folded petals of engineered gold, tuned to wavelengths that human eyes cannot see, but the universe has been whispering in for billions of years. In the tradition of Hubble and the James Webb Space Telescope, and alongside missions like Euclid, it has been given a simple mandate: measure the invisible scaffolding of the cosmos. Night after night, it stares not at nearby worlds or familiar constellations, but at vast congregations of galaxies known as clusters, bright knots of matter. Embedded in colossal halos of dark matter, the telescope's task is almost ascetic in its simplicity. It collects the faint glow of galaxies whose light has been stretched by cosmic expansion into the infrared, and sends the data back to Earth in silent streams of numbers. No one expects individual stars in those distant galaxies to stand out. At those scales and distances, stars blur into a diffuse haze, like grains of sand merged into a distant shoreline. The science is statistical. Measure the subtle distortions in the shapes of background, galaxies caused by gravitational lensing. Infer how much dark matter lies in front of them, and refine the story of how the universe's expansion has changed over time. It is not a hunt for miracles. It is a survey, repetitive, systematic, methodical. One of the survey's favorite targets is a massive galaxy cluster at extreme redshift. A titanic congregation of matter so dense that its gravity bends light into arcs and rings. In images, this cluster looks like a cosmic whirlpool. Bright elliptical galaxies in the center, surrounded by smeared ghostly arcs of background galaxies stretched into crescents. Astronomers call such structures gravitational lenses. They are nature's own telescopes, carved not from glass and metal, but from mass and curvature. When light from a more distant galaxy passes near the cluster, its path is deflected, sometimes split into multiple routes around the mass, magnifying and multiplying the background source. This particular cluster is valuable precisely because it is so heavy and so well placed on the sky. Its gravity amplifies the light from galaxies much farther beyond. Galaxies that would otherwise be too faint for any telescope to resolve. By observing it at infrared wavelengths, the survey can peer deep into cosmic history, tracing the web of dark matter that binds the cluster and measuring the geometry of the expanding universe. It is, to those who work with it, a trusted tool, a familiar lens through which the distant past can be statistically reconstructed. On the ground, the data arrive as they always do, long sequences of numbers. calibrated images, spectral files lined up in digital archives. Teams across the world specialize in decoding different aspects of these observations. Some measure the shapes of lensed galaxies. Others focus on refining the mass model of the cluster. Others compare the observations with predictions from large cosmological simulations. In one corner of this global effort, a small group is tasked with a more delicate role, studying highly magnified points of light that appear near the thin caustic lines of the lens, places where the magnification is extreme and fragile. Within this group, in a quiet office lit more by monitor glow than sunlight, sits a postdoctoral researcher whose job is to search for transient events, brief brightenings that might indicate a star in a distant galaxy passing behind a particularly sharp fold in the gravitational lens.
It's completely
Such events have been
metal
seen
poor.
before. Microlensing spikes produced when individual stars in the cluster temporarily amplify the already lensed light from a background star. Hubble once glimpsed such a star and gave it a symbolic name, an echo of Icarus. James Webb has pushed that frontier deeper. The work here is a continuation of that legacy, hunting for individual stars and galaxies billions of light years away. Their light magnified for a fleeting moment by the interplay of gravity and chance. Most days, the work is uneventful. The researcher scrolls through different images frames, where one epoch is subtracted from another to reveal only what has changed. Noise, cosmic rays, artifacts from the detector, the occasional supernova. The rest is filtered away. Algorithms do the first pass, flagging pixels that cross a threshold. Human eyes do the second, judging which of those flags might hide something real. The routine is numbing in its repetition, but it is within such repetition that the universe sometimes slips in a small disturbance. In one set of observations of the familiar cluster, taken years apart, the researcher notices something that does not quite fit the pattern. In one arc-thin, stretched image of a background galaxy, there is a bright point of light, slightly offset from the galaxy's center, with a spectrum showing the signature of a hot, massive star. In another arc, in a different part of the lens, but clearly associated with the same background galaxy, there is another point of light. It too is bright. It too has a spectrum. And at first glance, the two look almost identical. The initial assumption is mundane. Perhaps these are two different stars of the same type in the same distant galaxy, both coincidentally magnified by the lens. Massive stars are not so rare in star-forming galaxies. The universe is large enough to allow for coincidences. The researcher marks the case, labels it as a curiosity, and moves on. But some part of the mind, trained by years of squinting at subtle differences, does not let it go. Later, the spectra are placed side by side. Each is a rainbow smeared into fine detail, crossed by dark absorption lines where atoms in the star's atmosphere have removed specific colors of light. The pattern of these lines is a fingerprint, determined by the star's temperature, composition, surface gravity, and motion. In both spectra, the same broad hydrogen lines appear. The same helium features. The same subtle shifts indicate the same redshift. The same overall brightness, once corrected for magnification, implies the same intrinsic luminosity. They match so well that, aside from minor noise, they could be the same observation copied twice. Yet the two arcs in which these stars sit are not identical. The lensing geometry is different. The distortions of the background galaxy's shape are not the same, and the timestamps on the observations are separated by years. The telescope has returned to this cluster multiple times as part of its survey cadence, building up depth and time coverage. The first spectrum was taken in one observing cycle, the second in another, long enough apart that some stars in the same galaxy might have subtly evolved. What begins as a trivial curiosity slowly acquires weight. The researcher runs through the usual troubleshooting steps. Could this be a mislabeled file? A pipeline error that duplicated a spectrum and attached it to two different positions. The data reduction logs are checked. The raw detector frames are opened, their counts traced pixel by pixel. The machinery of modern astronomy, the software, the calibrations, the background subtractions, inspected like an engine being taken apart piece by piece. No obvious fault appears. In the language of the narrative, this is the moment where the universe clears its throat inside the data. Nothing dramatic, nothing explosive. Just a quiet insistence that 2 points of light in 2 different places on the sky carry the same story in their spectra. As if a single star has spoken twice through different mouths of the lens. Curiosity hardens into a question that cannot be dismissed. Are these truly 2 separate stars? Or is the survey gazing at the same distant star along 2 different paths through curved spacetime? To answer this, the team turns from images to models, from what the telescope sees to what gravity must be doing. Gravitational lensing is, at its heart, a problem in geometry. The mass distribution of the galaxy cluster, its galaxies, its dark matter halo, its unlit substructure acts like a warped sheet on which light from background objects slides and bends. By modeling this sheet, by assigning mass to the visible galaxies and to the invisible halo, astronomers can trace the routes that light rays must take from a background source to the telescope. Using sophisticated software, the lensing group feeds in the positions of the arcs, the shapes of the distorted galaxies, the locations of the cluster members. They adjust the parameters of the cluster's mass distribution until the simulated lens reproduces the observed arcs. It is an iterative process, guided by both data and physical constraints. For this cluster, the exercise has been performed before, many times. The models are already good, but now they are refined even further. With the positions of the 2 suspect stars added as additional constraints, when the model stabilizes, the paths of light can be traced backward. Rays are launched from the telescope, through the simulated cluster, and back into the distant universe, converging on the plane where the background galaxy lives. The 2 observed points of light, one in each arc, are followed along their respective geodesics. In the source plane, the 2 rays land nearly on top of each other. Within the uncertainties, they originate from the same region in the same galaxy, separated by no more than a fraction of a light year. Given the magnification and the inferred size of a typical massive star's environment, the simplest interpretation is that the rays come from the same star. This conclusion is unsettling, but still, it could be brushed aside as a quirk of modeling. So the team varies the model parameters. Slightly more mass here, slightly less there. Different assumptions about how the dark matter is distributed. The inferred origin of the 2 rays shifts a little, but not enough. In every reasonable configuration, the 2 lines of light converge. They do not diverge into 2 widely separated stars. They remain stubbornly, almost defiantly aligned. Only then does the team begin to examine the implied time delays. In gravitational lensing, not all paths are equal. Some routes through the warped spacetime around a massive cluster are shorter in physical distance or in gravitational potential. Others are longer, forcing the light to spend more time climbing out of deeper wells. General relativity predicts that these differences will show up as time delays between the arrival of signals from the same source seen along different images. Such delays have been measured before in the flickering of distant quasars and in the multiple images of lensed supernovae, and used to estimate the rate at which the universe expands. In the case of this star, the lens model returns to numbers, the arrival times for the 2 paths, relative to some arbitrary 0. The difference between them is not small. It corresponds to years, perhaps decades, of additional travel for one ray compared to the other. On cosmological scales, this is a modest gap, just a heartbeat in a universe billions of years old. But on stellar timescales, for certain kinds of stars, it is enough for real change to occur, for fuel to be consumed, for winds to blow. For neighboring stars to live and die, the realization does not come as a single dramatic outcry. It arrives as a gradual settling of facts into place. On one monitor, the younger, hotter spectrum. On another, the identical fingerprint. On a third, the lens model's depiction of 2 winding paths through the same cluster. One slightly longer, one slightly shorter. The implication is clear and quietly disorienting. The telescope is, in effect, seeing the same star at 2 different moments in its life, both arriving at Earth in the same human decade. A background star, born billions of years ago, has had its light split and delayed by the architecture of the universe. One stream of photons began its journey earlier, taking a more direct route around the cluster. Another stream left later, or passed through deeper gravitational wells, arriving only after wandering for extra years through curved spacetime. To the instruments, they arrive together. To physics, they do not belong to the same now. In the stillness of the analysis room, the star cannot be heard, yet its light has spoken twice. The data hint at a biography divided, a life seen both in its youth and in its maturity, projected onto the same sky. The universe has not broken any laws. General relativity allows such time-split images, but there is an emotional dissonance in realizing that a single point of light on a computer screen might be a star remembering its own birth offering. In two separate beams, two separate chapters of the same existence. The details, the implications, the full strangeness will come later. For now, there is only the first quiet recognition, somewhere beyond that massive cluster. In a galaxy whose own history is lost to distance, a star has been turned by gravity into a kind of mirror, reflecting itself across time. And on a small world far away, a handful of minds have just learned to notice. On a screen filled with numbers and calibrated noise, the star first appears as two simple curves. Each curve is a spectrum, a band of light stretched out and dissected into its constituent colors, like a rainbow laid flat and examined line by line. Across that band, dark notches run vertically absorption lines, where atoms in the star's atmosphere have removed specific wavelengths. To most of the world, they would look like nothing more than stray shadows on a graph. To those who have learned to read them, they are sentences written in the language of physics. The team lays the two spectra over one another. At first glance, they match. The same broad hydrogen lines, wide and deep, marking a hot, massive surface. The same helium features, carved like fine script into the continuum. The same overall tilt, indicating the same redshift, the same incredible distance, and the same expansion-stretched journey through time. In both cases, the light has traveled for billions of years. Both belong unmistakably to the same far-flung region beyond the lensing cluster. But as the comparison becomes more precise, small differences begin to surface. In the first spectrum, the light is harder, bluer. The peak shifted toward shorter wavelengths. The lines are sharp against an intense, high-energy background. It is the fingerprint of youth, a star burning at a higher surface temperature. Its outer layers still dominated by the primordial mix of hydrogen and helium from which the early universe was built. Trace elements appear only faintly. In astrophysical terms, it is metal-poor, chemically simple, like a voice still unused to complexity. In the second spectrum, taken from the other lensed image, the same pattern of lines appears, but the colors are subtly different. The overall shape is softened, the peak eased toward the red. The star is cooler, still luminous, but no longer at its earliest, most blistering intensity. And woven into the familiar hydrogen and helium features are new, narrower lines, signatures of heavier elements, of oxygen and perhaps iron, etched more strongly into the light than before. It is as if the same voice has aged, gaining resonance in new tones, while its basic identity remains unmistakable in the language of astrophysics. These heavier elements are metals, a word that, in this context, means anything in the periodic table heavier than helium. Stars are born almost entirely from hydrogen and helium, the simple products of the Big Bang. Everything else, carbon, oxygen, silicon, iron, the elements that build planets and bodies and the rocky crust beneath human feet forged later, in the deep furnaces of stars and in the explosive deaths of the most massive among them. Through nuclear fusion, stars gradually transmute their fuel into heavier nuclei. Through supernova explosions, they scatter those elements into space, enriching the gas that will one day form new generations of stars. Because of this, The chemical makeup of a star's atmosphere is a record of cosmic history. Young stars in the earliest epochs form from unenriched gas and are poor in metals. Later stars, born after many cycles of birth and death, carry more of these heavy elements in their atmospheres. Over time, as a single massive star evolves, its own nuclear processing and the mixing of its interior layers can slowly alter what appears at its surface. Stellar winds can carry newly forged elements outward. Surrounding gas can be polluted by neighboring explosions and then accrete back onto the star. The spectrum shifts line by line as the star lives and ages. The shock lies in the combination of these truths. The two spectra from the lensed star are nearly identical in identity, the same mass, the same redshift, the same broad character. They belong beyond reasonable doubt to the same object. Yet one looks chemically younger, hotter, bluer, lacking strong metallic lines, while the other looks older, slightly cooled, enriched by heavier elements that should not be present in such strength at the earlier phase. The universe has not handed the astronomers two different stars. It has handed them the same star with two different birthdays. There is a kind of discomfort that rises when the world does not match intuition. Here, that discomfort takes a precise form. Gravitational lensing is expected to split and magnify objects. It is not expected to split a biography. Around the table, the team pulls out models of stellar evolution. They estimate the mass implied by the star's brightness and temperature. Massive stars live fast and die young. The more massive, the shorter the lifetime. For a star in this distant galaxy to appear this bright, even after correcting for magnification, it likely belongs to the upper end of the mass range. Its life is measured not in tens of billions of years like the sun's, but in a few million. It spends only a brief time as a hot blue giant before swelling and changing, before perhaps ending violently as a supernova. Against that time scale, the modeled time delay between the two lensed images is not negligible. The lensing calculations suggest that one stream of light took a longer route through the cluster's gravity, arriving years or decades later than the other. The difference is small compared to the star's total lifespan, but it is long enough for measurable evolution, especially if external events have reshaped the environment. It is as though two photographs, taken years apart, have been delivered on the same day and placed side by side on a table. The face in each is the same. The expression, the lines, the shadows are not. Gravitational lens time delays themselves are not mysterious. Since the late 20th century, astronomers have used them as tools. When a distant quasar, bright, active galaxy nucleus powered by a feeding supermassive black holes lensed into multiple images by an intervening galaxy or cluster. Its intrinsic variability produces matching flickers in each image, separated by a delay. By measuring that delay and modeling the lens, cosmologists can infer the distances involved and derive the Hubble constant, the parameter that describes how fast the universe is expanding. Similarly, when a supernova explodes behind a lens, its light curve can appear in one image and then months or years later in another. An eerie replay of the same cosmic event from a different path. In almost all these cases, however, the lensed objects are extended and chaotic quasars, whose brightness surges and ebbs irregularly, or supernovae, whose entire existence as bright sources is brief. Their time-delayed multiples are used as global clocks, not detailed biographies. The delays are measured in days or months, sometimes a few years, rarely longer. They are important, but they do not normally confront the mind with the sense of a single, persistent object being seen at two distinct points in its own evolution. This system is different. Here, the lens has seized not a galaxy-wide flare, but a single star. A star with structure, a star whose spectrum acts as a high-resolution record of its state. The delay is long enough for the star's atmosphere and surroundings to have changed, yet short enough that those changes are subtle, almost trivial unless measured with the precision of modern instruments. On the detectors, on the CCD sensors chilled to cryogenic temperatures, both images arrive together. The electronics do not know that one stream of photons has been walking a longer path through curved space-time. They assign both to the same present, the same exposure, the same integer, timestamp. The screens show only now. The light reveals something else, that now is. In fact, stitched together from different moments in the star's life. Layered like pages pressed into a single frame, it is not a violation of Einstein's relativity. On the contrary, it is a direct consequence of it. Mass curved spacetime. Curved spacetime tells light how to travel. Different paths mean different travel times. All of it is predicted by the same equations that describe how planets orbit stars and how GPS satellites keep time. Nothing supernatural has occurred, yet the emotional response, even in a room of trained physicists, is difficult to dismiss. The star seems to be doing something living beings are supposed to do. Remembering a younger version of itself and showing that memory alongside its later self. This sense of unease is sharpened when the team examines the newfound lines in the older spectrum more closely. Some correspond to ionized oxygen, others to iron, and other heavy elements that, in such abundance, are usually associated with the aftermath of massive stellar explosions. These are the chemical ashes of previous generations of stars, thrown into space when those stars ran out of fuel and collapsed, triggering supernova that briefly outshone their host galaxies. In many galaxies, such enriched gas becomes part of the interstellar medium, drifting and mixing until it helps form new stars and planets. Sometimes, when a supernova blast wave slams into surrounding gas and dust, it carves out a nebula glowing shell or a filamentary cloud visible in emission lines. Light passing through such a region carries the imprint of this disturbed gas. In the younger spectrum of the lensed star, those imprints are faint. In the older one, they are stronger, more defined, as if the environment has been rearranged by some violence that occurred in the intervening years of the star's own life. This suggests a particular sequence of events. Somewhere in the star's neighborhood, another massive star has died, exploding as a core-collapse supernova. Its shock wave has crashed into the surrounding medium, heating and ionizing gas, injecting heavy elements into the local environment. That event may have brushed past the still-living star, altering the gas through which its light must travel, perhaps even accreting some of the enriched material onto its surface. The star continues to shine, but the light it now sends carries not just the story of its own internal fusion, but also the fingerprints of that nearby catastrophe. In that sense, the older spectrum is not only older, it is layered. It records both the intrinsic evolution of the star and the external history of its neighborhood. The younger spectrum, by contrast, shows the star before that, reshaping, before the nearby explosion, before the environment was salted with fresh ashes. The two curves thus do more than chart temperature and luminosity. They bracket an event, a supernova, whose light may or may not have been seen directly, but whose chemical and dynamical aftermath has nonetheless been etched into the surviving. Stars emitted light. Gradually, a metaphor begins to form around the anomaly. The astronomers, who spend their days immersed in equations and models, reach for a name that captures the feeling without pretending to solve the physics. They start referring to the object as an echo star, not because it literally echoes sound, but because its two appearances resemble the delayed repetition of a single cosmic statement in time. Within the collaboration, another, more poetic label surfaces, Mnemosyne. After the ancient Greek personification of memory, the name is not official. It does not appear in journals or catalogs. It lives in internal emails, in whispered conversations after seminars. In the quiet recognition that this star is different from the others, the nickname becomes a literary anchor in the minds of those who work on the data. Mnemosyne, the star that remembers. Mnemosyne, whose light carries more than one moment. Mnemosyne, whose spectrum reads like a confession delivered in two parts, in the older image. Those unexpected lines, those hints of a nearby stellar death are the key. They indicate that between the star's birth and its more mature state, its environment has already been scarred by violence. The star did not live in an isolated bubble. It grew and evolved in a crowded, volatile region of a young galaxy, where massive stars live and die quickly, enriching and disturbing their surroundings in rapid succession. The lensed light captures this context in exquisite detail. In the younger path, the confession is incomplete. The nearby death has not yet happened. In the older path, the testimony includes it. The light, in other words, has become witness. It testifies not only to the star's own internal evolution, but also to events around it that reshaped its sky. It carries across billions of light years the evidence of an explosion that no human instrument directly recorded, the trace of a stellar neighbor whose existence is inferred only from the chemical debris it left behind. Mnemosyne's spectrum becomes a layered record of origin, of change, of loss. For the astronomers, this is the first true confession extracted from the anomaly. Until now, the star's double appearance could be described in the language of lensing and time delays. It could be treated as a curious but ultimately geometric effect. With the recognition of the environmental changes encoded in the older spectrum, the narrative shifts. The star is no longer merely a point source being split and delayed. It is a chronicle, a before and after written in light, and somewhere in the quiet of the data center, amid the soft hum of cooling fans and the distant clicking of keyboards, a deeper realization settles that in a universe where light can be bent into multiple paths, a single star can, in a sense, remember not just its own youth, but the history of the space around it, and that, for a brief moment on a small world far away, those memories have arrived together, asking to be read. Almost lost in the noise, but statistically real. They hint at the presence of a surrounding nebula, gas in the star's vicinity that is being illuminated or ionized by something energetic. In the older image, those narrow features are not simply stronger, they are reshaped. Some lines shift in relative intensity. Others appear where none were seen before. At certain wavelengths, a low-level emission component seems to sit atop absorption, a subtle indication that glowing, excited gas now contributes more to the total signal. It is as if the fog around the star has thickened, brightened, and rearranged in the interval between the two epochs. To decode this, scientists draw on another chapter of observational history, the study of supernova light echoes. When a massive star explodes, its light does not simply radiate outward in a perfect sphere and fade. Some of that light encounters dust, clouds, and interstellar filaments at various distances and angles. It scatters off those particles, redirected toward different lines of sight. Because the scattered paths are longer than the direct line from explosion to observer, the echoing light arrives later, sometimes years or decades after the initial flash has faded. To a telescope, this can appear as expanding rings or arcs of light around the site of the supernova, slowly moving as the sphere of illumination sweeps through the surrounding medium. These echoes are not mere visual curiosities. They preserve in delayed form the original spectrum of the explosion itself. By observing them, astronomers have reconstructed the details of supernova that occurred long ago, effectively replaying cosmic events from archival light stored in dust. In some cases, echoes have even been used to reclassify historical supernova whose direct observations were incomplete. The same physics applies, in quieter fashion, to any intense outburst in a dusty environment. Light from the event can be trapped, scattered, and re-emitted by surrounding material, leaving lingering fingerprints on the spectra of objects embedded within or behind that material. If a supernova has detonated near Mnemosyne, shock waves and radiation would have altered the local gas and dust, reshaping the star's immediate environment. Ionization fronts would have rippled through the birth cloud. Dust grains would have been heated, destroyed, or reformed. The net effect would be a change in the narrow line spectrum seen along the star's line of sight. Viewed in this light, the differences between the younger and older spectra take on new meaning. The earlier spectrum, corresponding to the shorter light path, appears to show Mnemosyne before the full effects of such an explosion have propagated through its surroundings. The nebular signatures are faint, the ionized gas less dominant. The later spectrum, arriving along the longer path, reveals a more dramatically altered neighborhood. The narrow lines hint at denser, more turbulent gas, at stronger ionization. At the chemical remnants of freshly synthesized heavy elements, now suspended in the region, the universe has not only allowed the star's own evolution to be seen twice, it has preserved a before and after image of the violence nearby. Mnemosyne's light, split by the cluster's gravity and delayed by spacetime itself, appears to carry within it a composite memory, its own birth cloud, the steady burning of its main sequence life, and the death of a neighboring star whose shock has passed through its sky. In this realization, the metaphor that has quietly followed the object from its naming deepens. The star's light is no longer just a confession of internal change. It becomes a layered testimony, a record of both self and surroundings, written in a language of lines and continua. One part tells of an origin in metal-poor gas, of a young, hot surface still close to its primordial simplicity. Another part, delayed and enriched, confesses to a later time when the environment has been scarred and complicated by an explosion, by the injection of new elements, by the rearrangement of gas and dust. The anomaly that once seemed like an error in the pipeline now stands revealed as something more delicate and more profound, a star whose photons have been forced, by the curvature of the universe, to arrive in such a way that two chapters of its story are visible at once. Between those chapters lies an event that the star did not cause, but could not avoid being shaped by a hidden supernova, whose existence is inferred from the subtle shifting of spectral lines rather than from a sudden flash of light. And so, in quiet meeting rooms, and in the solitude of late-night analysis, a consensus begins to form. Mnemosyne is not only a lensing curiosity, it is an object that turns abstract concepts time delay, chemical enrichment, environmental feedback, to something almost tangible. Its light, once thought of as a simple stream of photons, now feels more like pages in a book that have been shuffled and overlaid by gravity. The task ahead will be to read those pages with increasing clarity, to separate the handwriting of the star from the handwriting of its violent surroundings, and to understand what this layered confession reveals about a universe that remembers its own past in light. In the beginning, the puzzle seemed contained, the twin spectra, the chemical differences. The inferred supernova, these could all, in principle, be nested comfortably within the known geometry of gravitational lensing and stellar evolution. The equations were unusual, but not unmanageable. Light followed curved paths. Stars lived in aged, explosions rearranged their neighborhoods. Mnemosyne was strange, but it was a strangeness with edges. Those edges begin to blur when the numbers are pushed harder, as more telescopes join the effort. The lens models become increasingly detailed. New constraints are added, the precise positions of faint arcs, the weak shear imprinted on the shapes of background galaxies across a wider field, the X-ray profile of the cluster's hot gas, the subtle shadow the cluster casts on the cosmic microwave background. All of these data feed into the same machinery, sophisticated codes that attempt to reconstruct the three-dimensional gravity, well, in which the light has been bent. Each refinement sharpens the picture of the cluster's mass distribution. Dark matter, invisible but dominant, is sculpted into a map of halos and subhalos, a web of density peaks and filaments that determine how space-time is curved. Within this reconstructed landscape, the paths taken by Mnemosyne's photons can be traced with increasing fidelity. The two beams, once followed only in broad strokes, are now described in fine detail, where they pass close to massive member galaxies, where they skim the shallows of the potential, where they dip into deeper gravitational valleys from these paths. The travel times of the photons are calculated again. Gravitational lens time delay has two sources: geometric length and gravitational time dilation. One path may simply be longer, adding extra distance. Another may plunge deeper into the cluster's potential well, where time itself runs more slowly due to the curvature of spacetime, delaying the light even if the geometric distance is similar. Both effects are accounted for in the models, as they have been for decades in studies of lensed quasars and supernova. Yet no matter how the parameters are tuned, a stubborn discrepancy remains. For the measured redshift of the background galaxy, for the cluster's mass as inferred from its lensing, its X-ray glow, and its influence on the microwave background, The delay between Mnemosyne's two images comes out larger than expected. The longer path does not lag by a handful of days or months, but by a span that, within the uncertainties, strains the standard cosmological model. This tension is not born in isolation. For years, cosmologists have been grappling with a quieter conflict, different methods of measuring the universe's expansion rate. The Hubble constant have yielded values that refuse to agree. Observations of the early universe, particularly the cosmic microwave background as mapped by experiments like Planck, imply one value. Measurements in the late universe using supernova, Cepheid variables, and lensed quasars as distance and time markers point to a higher rate. The discrepancy is small in relative terms, but statistically significant, and it has prompted debates about whether unseen systematics are at work or whether new physics modifications to dark energy, additional neutrino species, exotic early universe behavior might be required. Mnemosyne's time delay quietly touches this wound. If the lens model and the distance to the star are correct, the large delay appears to prefer an expansion history slightly different from what other probes suggest. It is as though the star's split light is offering an additional, oddly tuned measurement of cosmic time 1 that does not align perfectly with either of the existing camps. Some researchers argue that this is simply another hint that cluster mass models harbor hidden complexities. Others note that the delay calculations dip into the same combination of geometry and expansion that underpins the broader tension. In meetings and in preprints, care is taken not to oversell the connection. One star cannot resolve a debate that spans data from countless galaxies and epochs, but the fact remains in the best available reconstructions. The difference in travel time between Mnemosyne's two beams does not quite add up. The universe seems to be taking a little longer, or curving a little more deeply, than the simplest picture allows, while this larger cosmological question simmers another. More intimate tension emerges from the stellar side of the problem. The mature image of Mnemosyne, the one associated with the longer path. The enriched spectrum, the altered surrounding gestelles, a clear story about the star's evolutionary state, its temperature, luminosity, and spectral type. When combined with stellar models, suggest a massive star approaching the end of its main sequence life. Such stars are not patient. They burn through their hydrogen fuel quickly. For a given mass, modern stellar codes can predict, to reasonable accuracy, how long a star spends in each phase, when it will swell, when it will alter its surface composition, when it will die. Those calculations are applied to Mnemosyne. Its mass inferred from its brightness once lensing magnification is accounted for. This places it in a regime where lifetimes are measured in a few million to perhaps tens of millions of years. The difference is seen between the younger and older spectra, the slight cooling, the increased presence of heavier elements. The environmental changes are consistent with evolution over a significant fraction of that span. It is as if the narrower, cleaner spectrum shows the star in an earlier, relatively untouched chapter. The broader, enriched one shows it approaching the last pages. When the modeled time delay from the lens is folded into this picture, a paradox emerges. If the longer path represents light emitted after the shorter path's photons left the star, and if the evolutionary changes between the two spectra require a certain number of years of internal burning and external reshaping, then by the time the younger light stream reaches Earth, the star itself, in its own frame, should already have moved beyond that earlier state. It may have swelled, shed mass, or even collapsed into a remnant neutron star or black hole depending on its mass and environment. Yet the telescopes now see both. On the same screens, in the same observing runs, in the same human decade, two epochs coexist, a star still wrapped in the relative simplicity of its youth, and a star seasoned by fusion and will pie the echo of a neighbor's death. The instruments, obeying the indifferent logic of detection, registered both as present. There is no true contradiction in the physics. General relativity allows for such arrangements. Light does not care about simultaneity in the human sense. It cares about the paths available to it. One beam left earlier, another later, and the warping of spacetime has arranged their arrivals so that distant observers encounter them together. For the star, those moments are separated by real, lived time. For the telescopes, they are compressed into a single observational window. The dissonance is emotional rather than mathematical. Astronomers, accustomed to thinking of stars as remote, but singular, each one occupying a place on the Hertzsprung-Russell diagram, each one progressing inexorably from birth to death, now confront data that invites a different mental picture. Mnemosyne is not just a point on a track. It is a track scene from two angles at once. The metaphor that once seemed poetic hardens into a literal description. The observers are witnessing both a beginning and a late-life confession from the same object, caught by the structure of the universe and delivered as one in private. Some describe it as like looking through an old family album and finding, improbably, that two photographs of the same person, one as a child, one near the end of life, were taken on the same day. The physics explains how the album was assembled. The feeling, however, remains uncanny, as the lens models are pushed to their limits and the stellar evolution tracks are scrutinized. A few theorists begin to look elsewhere for answers. Beyond refinements of existing ingredients,